So, the area problem. Well, basic geometry, elementary school geometry, find the area of a rectangle. That's simply the product between the length of the base times the length of the width, or the height, rather. The area of a triangle, area equals base times height divided by 2. What else do we have for area? I mean, area of a circle, pi r squared. Well, you had a few ways to come up with that equation, right? With that formula. But let's keep this simple. Now, what if we extend this, to find the area of a, I don't know, of a hexagon, for example. So, well, you might know of a formula that says to get area of a hexagon or another polygon, that's multiply the perimeter times the apotheme, where the apotheme is this distance from the center to a point that forms a 90-degree angle on any of the sides. So that distance times the perimeter is equal to the area of a polygon. Well, we're not going to use that idea this time. However, we're going to do some intuitive ideas. So in this case, we are going to simplify the area of this hexagon by partitioning this into areas of triangles. See what I'm doing here? We are partitioning this into area 1 plus area 2, area 3, area 4. So finding the areas of 4 triangles add up to the area of the hexagon in this case. All right, and well, we can repeat this process to find the area maybe of a heptagon, a decagon, or a geometric shape with 20 sides, 100 sides, But I mean, what we do is simply chop it into simpler regions, which in this case is triangles, because we know formulas to find areas of triangles. Find the areas of those triangles, add them up together. That's the area of the hexagon in these simpler cases. However, well, that's not that hard to do. I mean, with knowledge that we have for now. I mean, because we have formulas to find areas of triangles, use them, and just get the results. What if we want to find the area of a shape like this? I mean, you can find the area of only this portion, the rectangular form, the rectangular region. But what about this curve right here? I mean, unfortunately, we don't have, we have some rules that measure distances for certain curvatures. But in this case, we would need rulers for every single curvature. You would have to design a ruler so you can exactly measure the distance, and even doing it that way, it's not going to give us the actual area. What if I want the area under this curve, for example? All right, what about the area of this? Different weird shapes. Well, this is what we're going to learn in this part in this course, but mostly like the areas of these shapes, sort of. You're going to learn that more in depth next semester in Calc 2. All right, to get the simpler case, let's consider finding the area under the curve f of x equals x squared over the interval 0 to 1. So here's the graph of y equals x squared on the interval 0 to 1, and in this case, well, this shaded area in blue, it's the area under the curve. However, how do we get the area of that shape? Because in this case, it doesn't look like a triangle, it doesn't look like a rectangle, it doesn't look like a geometric shape for which we know a formula for. All right. In the same way that we went from triangle to hexagon, polygon. Well, we're going to do something similar here. Add S1, S2, S3, S4. So partition the area into simpler area. However, that is not going to solve the problem, because even when we partition this into more than one area, focus on this one for example, we still have this shape. We have a curvy shape for which we don't have we don't have a formula to find the whole area under the curve. So here is the thing: the intuitive way, or the intuitive idea, is to make this in this particular case, these four regions, turn them into rectangles. This rectangle, that rectangle, that rectangle, that rectangle. 4 rectangles. So that's area 1, area 2, area 3, and area 4. Alright? However, there's a little issue here. There's a little downside here when we're using rectangles to find the area under the curve y equals to x squared. I mean, check this out. Here, sure. And let me highlight it again, even though it's already highlighted. Here is our area under the curve. That's covered already by the rectangles here. However, the issue here is, do you see that extra area here? Here. 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 And here. Well, if we estimate the area by finding the area of those 4 rectangles, well, why do we do that? Because we know how to find the area of a rectangle. Just multiply the length of the base times the height. That's all we do. However, because we have some extra area outside of the region that we want, if we do it this way, this will actually overestimate the value of the area that we want to calculate. All right? So there's a couple of ways to improve this calculation. Well, in this case, for the general case, for the easy case, so to speak, we just partition the area into 4 rectangles. Okay? However, we can find a better estimate of the area if we partition the region 0, the interval 0 to 1, into more rectangles, like 1, 2, 3, 4, 5, 6, 7, 8 rectangles instead of 4. 1, 2, 3, 4, 5, 6, 7, 8 rectangles instead of 4. Alright? And well, compare these two areas right here. Again, let me highlight the area that we want. That's the area that we want to find, the area under the curve. And well, let me highlight again with pink that area that goes outside, that it's actually overestimating the calculation that we want. I mean, see the difference? I mean, just visually, it looks like, yes, even though we use more rectangles, but did you see how these smaller rectangles is actually smaller area than this overall smaller area outside of the graph? So we're somehow fixing the issue of the overestimation by adding more rectangles, but still it's not an accurate area. And in this case, notice, check this out. Whenever, so just so when we solve the actual problems, doesn't freak you out when we talk about right endpoints, left endpoints. So in this case, for the first situation, we're using left endpoints. What are those left endpoints? Well, this left endpoint of the rectangle, of the first rectangle, so this is the first rectangle, this corner right here is the left endpoint of the first rectangle that is intersecting with the graph of f of x. Let's look at the second rectangle. Right here, this point is the left end point of the second rectangle, left end point of the third rectangle, right end point of the left end point, left end point of the last rectangle. All right. Another way to estimate these areas is to instead use left and right end points instead. And using right end points, so check this one. This is a right end point because it's in the right of the. Oh, wait a minute. This is the reverse. These are right. Yes, right. Yeah. No, and the reason why it's confusing because and well, I always got this confusion when I took the class. I mean, when I'm seeing the area going outside of the of the curve towards the left, that's what makes it confusing. But I mean, really, we're using the rightmost endpoint. So in this case, using left endpoints, this is the left endpoint, left endpoint, left endpoint. You know. However, check this out. So this is the area that we are obtaining using using left endpoint. However, one thing to distinguish between the estimation via right endpoints versus left endpoints is instead of getting some area outside of the graph, that we don't want that extra area. In fact, when we do the other endpoints, the left endpoints, we are getting instead these gaps for which we're not considering this area, right? These void spaces here, if you want to call them in a different way. So, in this case, comparing these two values, I mean, compare the areas of these rectangles versus the areas of those rectangles. The first one, it's going to give us an underestimate versus an overestimate. All right. And well, I'm using the example from the textbook. In this case, they are calculating the areas of both the underestimation using left hand point, that is, rectangles inscribed inside of the function, and the overestimate using the rectangles that go outside of the function. For now, don't worry about how they got these results. I mean, this is just a visual with some numerical values, ultimately just to determine that the actual value of the area under the curve has to be between these two values. We're gonna learn soon how to get those values. Don't worry. But I mean, all I want you is to see the bigger picture here. So, what's the intuitive idea about partitioning and improving the area, right? The value of the area. Are you guys following me up to this point? All right. Can we make a better estimate? That's the question, and of course we can. What if instead we partition our region using 10 rectangles, 30 rectangles, 50 rectangles? Did you see how adding more rectangles of a smaller base actually reduces that overestimation value? At the same time, it does the same with the underestimation. It actually, in either direction, it actually gets closer to the actual value of the area under the curve. So, in the same way, again, we want to remember how we use the limit definition to find the slope between 2 points on a curve. The idea is to make the distance between those 2 points as smaller as possible, in a way that the secant actually became the tangent. You know, we took a limit as the delta x or h actually was 0. So in this case, in a way, we are going to find another limit. So, and in this case, let me ask a question. How many rectangles do you believe is going to give us the actual area? Do you think 50 is the actual area? How many? How many?
Infinitely.
Infinitely many. All right, but that's kind of weird, isn't it? It's kind of weird to think about infinitely many rectangles, because the more rectangles, the base of the rectangle gets smaller and smaller all the time. So if I have infinitely many rectangles, what's the base? Isn't that really like 0? So in a way, we are going to treat this problem as a limit problem, and in this case, treating that distance delta x to be 0, or the number of rectangles to be infinity. So either as a limit equals 0 or an infinite limit. We're going to do that in the next section. Right now, we're just looking at the construction of the idea. All right, and well, we can generalize this idea for another function, of course. I mean, think of this function, this weird function, and by the way, this contains right endpoints, some number of rectangles, 1, 2, 3, 4, 5, whatever. That's gonna, how many rectangles? Well, that's gonna be told in an actual problem. All right. So here is a formula to calculate that. Well, but I'm going to explain where is that formula really coming from. So number one, we need to actually find the areas of these rectangles. So for example, if we do A1, A2, A3, A4, A5, A6, AN, and that's going to be for the number of rectangles. Guys, those of you who are taking pictures, please stop doing that. Write your own notes. So for example, the area will be the addition of area 1 plus area 2 plus area 3 plus plus area n. All right, the area of the nth rectangle. And well, in this case, I'm just going to use, this formula may change. This formula may change based on whether we use right endpoints or left endpoints. Well, in this case, actually, I have like the wrong formula. Maybe I should disregard this term right here, because in this case, we are using, in accordance with the picture right here, we are using right endpoints, and the right endpoint, it's actually, the first right endpoint is actually related to f of x1. Well, notice these rectangles. All these rectangles have the same length of a base. That's let's call this a delta x. This delta x is the same as this delta x. This delta x is also the same as the delta x. So that's the idea, to find areas of rectangles with the same length of the base, and all we do to find the area of the rectangle, multiply the base times the height. But how do we get the height of the rectangle? The height of the rectangle is the intersection between the right endpoint corner of the rectangle and the function. So all you do is really evaluate at f of x of y, and that subscript I, that index I, is related to maybe the first rectangle, the second rectangle, the third rectangle, etc. So for example, over here, if we find the area 1, that's going to be base times height, base 1 times height 1 plus base 2 height 2 plus base 3 height 3 plus plus base sub n height sub n. Well, depending on the number of rectangles that we have. All right, but in this case, the length of the base, did you notice it's the same? It's delta x. Well, so in this case, I'm going to multiply the height first. The height, which is given by f of x1 times base 1, which is delta x, it's always delta x plus f of x2 delta x plus f of x3 times delta x plus plus f of x sub n delta x. And notice a common factor of delta x. So delta x is it's a common factor. Oops. That's going to be f of x1 plus f of x2 plus f of x3 plus dot 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 plus f of xn, depending on the situation. Doesn't that look like the formula that we had here? Because delta x is the same for the rectangle. So we partition the region into rectangles of the same width to make our calculation easy. Of course, again, looking back to this right here, well, using the idea of the rectangles, well, of course, that's going to give us an inaccurate area right here. However, maybe not in calculus 2, maybe in because I teach calculus 2 and we don't cover the numerical methods to evaluate integrals. So there's even better approximations for finding the areas under the curves in a very similar intuitive idea that it is for the rectangular, for the areas of rectangles. Instead, you will find the area. Instead of finding areas below rectangles, actually areas below trapezoids. Do you see how these trapezoids instead would give us a better it's almost the same area using areas under trapezoids instead of using areas under triangles. And then there is another rule that it's even a stronger rule. It's called the Simpson's rule. And the Simpson's rule, it's actually about finding areas under parabolas. And these parabolas actually look closer to the area under the parabola, and actually that improves the calculation for the area. But well, that's something you're going to learn in further courses. In the meantime, we're just going to look at the simplest case, which, yes, I understand it's not going to give us the best approximation. So in this case, it's just by finding areas under rectangles. And well, here is a justification of where are we getting this formula from. I guess this is going to make more sense once we look at the examples. And I have one example here. Alright. Oh, by the way, I needed to mention this delta x is the difference between the endpoints of the interval over we want to find the area for, but then divided by the number of rectangles. So this is very important, and you'll see how is this going to work in the first example. All right. Estimate the area under the curve of f of x equals x squared plus 1 on the interval 0 to 4 using letter A, 4 rectangles, but in this case left end points. All right. So number 1, we want the area under the curve. 1, 2, 3, 4. 1, 2, 3, 4. And so we want to find the area under the curve y equals x squared plus 1, which is going to look sort of like this. I'm going to make it look like this so we can so 1, 2, 3, 4, so we can easily look at the region in this case. All right, I know this is inaccurate because, well, 1 squared should be equal to 1, 2 squared should be equal to 4, 3 squared should be equal to 9, but that's so it is easy for me to draw the rectangles here. All right, so in this case we are going to partition this area into rectangles whose width is delta x given by the limits of integration over n. That is delta x equals b minus a over n, where this is b, this is a. That is 4 minus 0 over the number of rectangles, which is 4, and that's 4 minus 0, which is 4 over 4. That equals to 1. So we're going to find areas of rectangles that of width equal to 1. However, careful, because we are using right endpoints. So when we use right endpoints, for right endpoints, that's going to be the first rectangle. And notice in this case, the right endpoint is going to give us an overestimate because we have some area outside of the curve. Yes?
When you say 0 is b, then what's 4 minus 0?
Oh, that's the lower limit. 0, 4 minus 0, b minus a, which is... Oh, yeah. I see what you mean. No, this is backwards. Thank you. A and b, right? Yeah. Otherwise it's negative, and well, no, you don't want a negative area here, right? And well, the second rectangle here, another right endpoint.
Shouldn't it be left endpoint?
Did I say left? Oh yes, I said left endpoint. My bad. Okay, left endpoint. Yes, because I wanted to get the underestimate first and then the overestimate in order. Thank you. And let me also fix this from A to B. And so that's left endpoint. Left endpoint. Left endpoint. And left endpoint. So we are integrating from, or finding the areas from 0 to 1, 2, 3, and 4. So we need to compute the areas of 4 rectangles in this case. Alright. Of course, that's not going to give us the most accurate areas. Do you see all the void that we have in here? So we're going to get a value of the area that it's a lot less than the actual one. Alright. So that means that we need to evaluate f of 0, f of 1, f of 2, and f of 3. It involves those 4 calculations. So if we label this as area 1, area 2, area 3, area 4, that's the total area equals area 1 plus area 2 plus area 3 plus area 4. I mean, you will find out how these calculations are going to go really simple. But I mean, these are deceivingly simple because I mean, it's important to understand what about the number of rectangles, how do we set up the region, and keeping in mind whether this region is going to go left endpoint or right endpoint, which is the mistake I just did. All right. So that is the area of this rectangle. So what is that's going to be, well, f of 0 times delta x plus f of 1 times delta x, f of 2 times delta x, and f of 3 times delta x. Well, in this case, delta x is a common factor, and all we have to do is evaluate f of 0 plus f of 1 plus f of 2 plus f of 3. Alright? So, delta x, we just found what delta x is. Isn't it 1? We got that from the beginning. That's 1 times f of 0. That's where we use the actual function that we're working with. That's 0 squared plus 1 squared plus 2 squared plus 3 squared. In this case, 1 times 0 plus 1 plus 4 plus 9. Add these numbers. 9 times 4, that's 13 plus 1. Isn't that a 14? And times 1, that's 14 units squared. And well, we just say unit, we don't say centimeters or... Oh, shoot. Yeah, because I was thinking of... Thank you. I was still thinking of the original function that we were working on. So that's going to be, okay, 0 squared plus 1 plus 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1. Well, that's going to be 1 times, okay, this is going to give us a 1. 1 squared, which is 1 plus 1, that's a 2. 2 squared, which is 4 plus 1 is 5. And 3 squared, which is 9 plus 1, that's a 10. Add these numbers together, so that's 10 plus 5, that's 15. And plus 2, that's 17 plus 1, is that 18? 18 units squared. So that's actually the underestimate due to the areas that we have here below, that we're not considering these little pieces of emptiness here. Now let's do the other region using an overestimate, and that is the right endpoint. So let's see. For right endpoint, and let me do the whole graph again. So that's 1, 2, 3, whatever. 1, 2, 3, 4, 5. Okay, so I just need 4. So in this case, graphing the function like this, and we're going to use right endpoints this time. That is, this is the right endpoint, the first right endpoint. No. And this is the second right endpoint. Third right endpoint. And fourth right endpoint. Whoops. No, that's not good. So let me go all the way here. Oh yeah, that's gonna look a lot better. So you can see the overestimation this time. We have some area outside of the curve y equals x squared plus 1. What do we need to calculate this time? Well, again, these delta x's are 1 unit, alright? That's the base of the rectangle, and it's the same for all rectangles, even though, well, visually it's not a perfect picture, but I mean, that's how we're partitioning these rectangles. But in this case, to find the heights of the rectangle, we need to evaluate f of 1, f of 2, f of 3, and f of 4. Alright, finding the area, under the curve, or well, the estimated of the estimation of the area under the curve. That's delta x times f of 1 plus f of 2 plus f of 3 plus f of 4. Well, the delta x, again, it's the same. That's 1 times f of 1, which is 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. And let's just simplify this to find the area of those 4 rectangles using right endpoints and get the estimate. Well, that's 1 times 1 squared plus 1, that's a 2, plus 2 squared, which is 4, plus 1 equals 5. 3 squared, which is 9. 3 squared, which is 9, plus 1 equals to 10. And 3 squared, oh yes, that's 10. And 4 squared, which is 16, plus 1, that's 17. Alright, 17 plus 10, that's a 27 plus 5. Is that a 32? Plus 2, is that a 34? 34 units squared. And well, here's where we need to compare these two results. This means, I mean, look at the second result. The second result is an overestimation because we're considering these areas that are going outside of the region. The first result is an underestimation because we're not considering these gaps right here. So this means that the actual area must be somewhere between 18 and 34. And I mean, the range of values is pretty wide. Why is it pretty wide? Well, that's because we're just using 4 rectangles. If we were using more rectangles, say 8 rectangles, well, that would have been taking forever to calculate. It would be taking a lot of time, but I mean, it's doable. We would have obtained a smaller number here and a smaller number there, actually closer to a center value. And be careful, we cannot just say, oh yes, it's going to be the average between 18 and 34. No, that's because this region is not perfectly symmetric. So for now, well, we're not going to care about what that value is. All we're doing is computing areas using right hand points, left hand points, so you can see the difference between the estimations. Question?
How come it's less than or equal to instead of just less than?
Less than. Oh yeah, less than, because it's an estimation, right? Thank you. Yes, that's true. So that's the intuitive idea. Of course, we're going to keep constructing this to come up with a more refined idea.